Okay, so the project that I've been working on is called Live Bootstrap. Anybody possibly heard of it? I didn't start it. It was started a long time ago by a bunch of smart people, but I joined a couple years ago, and I'm gonna tell you all about it. First, as I mentioned before, I'm from Seattle, but I spent half the year in New York. So I went to the Seattle Handmade Meetups earlier this year. I also did this presentation. There were a lot of questions. It went on. Hopefully, it won't go as long as it did, but I'll get right into it. Okay, so this is really truly in the spirit of handmade. We want to be able to build our software from source code. And so we use compilers, which is also software. And so we want to build our compilers from source code. And so you ask the question, how do I build GCC 13.1? And the answer you often get is, well, get the GCC source code and compile it with GCC. And you're like, well, I'm not sure that's fully satisfying. But it's like, how do I make yogurt? Start with milk and add yogurt. Well, okay, well then how do I get the yogurt? But for practical reasons, most people are fine with this. They don't need the compiler, and then, and if you did, you start asking, well, how would I compile GCC if I didn't have GCC? And so there was an effort to sort of retrace the history of the compilers that were used to build the GCC before we had GCC 13.1. So the idea is that you shouldn't have to have any pre-built software at all. Now this isn't technically possible, and I'll talk about that. But if you look back on how GCC 1.0, or the original one, was built by Richard Stallman, it was built probably with the Pastel compiler. I couldn't find any reference to what compiler he originally used, but also with Linux, it was built on the Minix operating system. So there wasn't really open source software back there to build your open source with, so they had to bootstrap off commercial software. And then they started building this chain of newer and newer versions of software, starting from way back when. I mean, if you even go back further, like it started with guys like flipping switches on mainframes or putting punch cards in directly into the computer. A group of developers started this Live Bootstrap project 7, maybe around 8 years ago. And Live Bootstrap is a project to basically try and build a full operating system from the grassroots, and it includes in it as submodule called Stage 0 POSIX, which is sort of the initial phase of building this operating system with the earliest, the most primitive kinds of compilers you can think of. And I'll talk about what that actually is. But as I mentioned earlier, you can't technically take a PC and put only source code on it. You need to start with something. The PCs use EFI now, which is a whole software suite, but they used to, and most computers now can still boot off the BIOS, which is taking one sector off the first sector off the hard drive, putting it into place in memory, and jumping into that sector. It's a 512 byte. So you at least have that mechanism. And so we started with this idea that, well, let's take the smallest possible boot sector program on the hard drive, and then everything else is source code. So the tiniest possible program to sort of kick off the process, and then start building compilers of the simplest sort, starting with this tiny program, which is currently down to 200 bytes. So most of that sector is actually just empty, and there's a program that just takes, and it starts off with a tiny little bootloader and a hex compiler. So all it does is convert hexadecimal, ASCII into binary, and then sort of progressively building up bigger and bigger and more powerful compilers. So it starts off with this hex 0 and then builds this hex 1 compiler, which all it does is have like some labels in it. It has the ability to have jump labels. And then hex 2 has like a variety of different relative and absolute types of labels that you can compile into your still hexadecimal raw code. That in turn is used to build an M0, M1, and M0 and M1. Both the M0 and M1 are macro compilers, so they're like macro assemblers. They simply substitute macros, which are like kind of like assembly, but just search and replace type. And so you'd have an opcode and then some hexadecimal after that. And then M2 is a primitive subset of C, and then that would build this MES-CC, which is, M2 actually builds a scheme interpreter, which then runs this MES-C compiler, which then is used to build TinyCC, and then starts up the GCC chain, starting with 404, and then progressively building up to GCC 13.1. And like I said, up to MES-CC, it's coming from, up to M2 coming from the Stage 0 POSIX project. But if you think about a operating system, it's not just compilers. What are the compilers running on? What's actually launching the compilers? You have a kernel, which has a shell and libc running on it. So you actually have, it's simultaneously building up a kernel to a phase of kernels, and then shells, which get more and more progressively powerful as it goes along, and libc versions, which get more and more powerful. Also, it starts building tools along the way as needed to sort of build up the operating system. Okay, so my contribution in a couple years ago now, they were just running this directly on a kernel, which you had to provide. So you would have to bring your own Linux kernel image, and it would launch with QEMU directly into the kernel, and then it would launch it would have a initial RAM drive, and it would start running the whole process. And they plan to build a kernel someday, but they're like, well, someday we'll do that in the future. And I was like, well, that's kind of cheating. I mean, you're assuming like this 4 megabyte binary program already to sort of launch the whole thing. And so I looked at the first hex 0 compiler that they had, and I'm like, this really only uses like 4 or 5 system calls. How hard can it be to write a kernel that just implements these system calls? And so I started working on this tiny little boot sector kernel, and I just kept on adding more and adding more into it until eventually it could actually run TinyCC and the shells and everything. And it's eventually became this 4 kilobyte minimal kernel, which is Linux compatible. All the system calls are Linux compatible. And once we get to TinyCC, we're able to build another kernel called Fuix, which is also Linux compatible, but it's much more powerful, and it's written in C. The kernel I wrote is actually written in hexadecimal. So it was, I had to kind of convert all of the opcodes into hexadecimal manually, because the only thing in the boot sector that could compile this thing was a very small hexadecimal compiler. So just to bootstrap into a very small kernel, that's all we had. So after the running this and building the next kernel, we'd actually jump into the next kernel, and then when Fuix is used to build the next Linux, the first Linux version, we live jump into that kernel. And I wrote the tools that did that. So just to show you what the hexadecimal looks like, it does have comments, but otherwise it's just hex versions of opcodes, which, this is the first instructions it runs to sort of set up the registers and then eventually jump into the main code. So this builder hex 0, it's actually a kernel, but it does have a tiny built-in shell and file system and the ability to load source code into the file system, and it has a small hexadecimal compiler. And then it's used to build other executables, which it then can run those other executables. But it starts off with the trifecta of a compiler, a shell, and a kernel, all in 4 kilobytes. So the whole system is currently 32-bit. We have a 64-bit version that we're progressively building up. We also have a UEFI version that's in progress. Those are kind of going slowly. There's a lot of programs that don't have 64-bit versions. Like the MES compiler is only 32-bit, but we're chipping away at it and eventually want to get to, in the 32-bit version, it does build up a full operating system, and that operating system is used to boot some, it bootstraps GUIX, I think I'm pronouncing that right. And then I think there's some work to build up Nix OS from that as well. So you have a full source code modern operating system all the way down, starting from a 200-byte program. And that's it. I could show you it actually running, but it's just a bunch of text flying by the screen, so I don't know how useful that would be. Okay, well, this is it actually running, and it checks out the code, and basically this whole thing downloads all the source code, assembles a disk image, and then launches it. And here it's actually loading all the source code into the kernel, and then we'll start compiling after that.
What stage is it at now?
It's in the Bork-K kernel. It's running the shell, and it's these commands are actually it has a shell which has a source command, and then it has the code the actual source afterwards. So it's actually feeding in the source code directly, kind of like a here doc in a bash shell. So it's actually loading the code into the kernel right now. And like loading the Linux source code takes like a minute or so. So this isn't actually all that exciting. I don't know if I have this. Before that, I think I ran it earlier, so it might be. So here's you can see it actually running some of the commands and the compilers when I ran it earlier. So after it loads the source, you can see it starts to run a shell and starts compiling hexadecimal, hex 0, hex 1, hex 2. It builds the cat command, and then it starts like concatenating programs together and building them and building the M0 macro assembler, and then it keeps on going. All right, any questions about that besides all my finances and
So I guess the first part is really fast, and it only gets slow once the code gets like, when you're bringing in like all the Linux kernel Because I was curious what was like the slowest part, but it just seems like naturally, as things get more complicated, those next stages that you bootstrap just have so much more code that the end stages just kind of dominate it all. Is that, or, because I was thinking maybe the first stages would be slow because they're not optimized like the later GCC could do, so they would run slow, but it seems like it's just the amount of source code that happens later dominates. Does that sound right? Or?
Yeah, so just loading source code off the disk with BIOS routines is very slow. And so there was another guy that came in and optimized it to use like LBA in multiple sectors and all this. But here's where you can see the actual speed of these initial programs. Like they're pretty fast, relatively fast. It's not until it gets to the scheme stuff that it really slows down. And that's because it's like a primitive version of C used to build a scheme interpreter, and then this massive ball of scheme code to try and, someone wrote a C compiler in Scheme for some reason, and it's the only one that we could use that actually is relatively powerful. Now there's another guy who's taken our M2 compiler and TinyCC, and he's kind of like built up all the way between those two. So we stay in the C world, and he's trying to get that integrated in so we can get rid of the scheme. But once it hits the scheme, it just it stops. And it takes like 15 minutes to get through compiling TinyCC with the scheme. But it runs like, it builds like, 40 or 50 tiny small compilers in like a few minutes, and then it hits scheme and just dies. But it'll get there, but we obviously don't have enough time to sit and watch it do this. But
from start to finish, how long is it?
so now it builds up, and I'm just gonna go over to another screen here. I'm gonna show you how much stuff it's building. So this file, parts.rst, is at the root of the live bootstrap. It shows you all of the different steps. And there's dozens and dozens of these. And it goes on. And especially with the autoconf, it builds multiple versions, because like every time they revved autoconf, they required like the previous version. And so it ends up taking like 13 hours or something to go through all of these. And things like GCC take forever to build from scratch. Python takes forever. But hopefully that's in the spirit of the handmade software, because it's truly handmade.
Yeah.
So most people would think of C as a low-level language, and they would think of Scheme as, it's got a garbage collector, probably it's maybe a high-level language. So I find it interesting that for this initial version of this process, someone decided to go up to Scheme and then come back down to C land, and it's slow. That's obviously the downside. But they probably made that choice for a reason, and I'm guessing that reason is that they felt that was a good way to express a compiler in a relatively relatively small amount of source.
The answer, though, is because it's actually it's a Scheme is kind of like a Lispy type language, and implementing a Scheme interpreter is actually not as difficult as a C compiler. Mm-hmm. So someone already had the C compiler in Scheme.
In the root, if you do manage to replace that part of the process, it would be all C all the way, or would the Scheme get replaced by some other intermediate?
It would be all C.
It would be all C. I know that the people who are interested in languages like Forth also make claims about it being good for this kind of bootstrapping
Yep.
process.
Yeah, there's a boot sector fourth.
Yeah. Do you have you looked at that kind of stuff at all?
The I'm not that well versed in fourth, and I find it a little bit confusing to me because I guess I'm not that smart. But the problem is that there isn't. You can do some cool stuff in fourth, but there just isn't the existing software chain of someone wrote an assembler and that can then. And all of these are multi-platform, so there's like a RISC version and a ARM, and so and conceptually it's a fine way to start. It's just that no one's done enough in that world to. But in primitive versions of C and so forth, there's a lot of different software out there, so we're able to sort of cobble that together. But starting just from fourth, you still have to write an assembler, you still have to do all that stuff, and no one's bothered to do that. But from the very beginning of starting, like fourth is built so it can start really, really slim, and you can, and then you can start building up slowly from there. It's just no one's done it. I spent a little bit of time on a boot sector Lisp that also was tiny. And I'm like, well, now I can start building up things. But then it was like you still didn't have primitives for like writing to the hard drive and doing all these other things. And so like I could use a Lisp to create like an assembler. But then how would I get it into memory and all this stuff? It was like I still didn't have all the primitives I needed. And so I was like, well, I can get really far and I can do abstract stuff, but I can't do any low-level stuff, and I still need to do all the primitives. So it didn't work.
Another question is, why choose to do live reloading of the kernel code with kexec? Why not just build a new image at each stage and then run that image separately? It seems to me like you're introducing complexity with like replacing the kernel code on the fly. That might make it harder to understand what's going on, but there's probably some reason to do that.
Well, part of the reason is just that the mechanisms for booting through a RAM drive image were more practical than sort of writing a file system to the hard drive. Because remember, we have all of our source code on the hard drive to begin with. And so then like somehow writing it back down to the hard drive and then rebooting. I actually did do it that way to begin with. So I did reboot the computer and eventually got to the point where like it didn't, I don't remember all the details, but it became too difficult to do it that way. And it just made more sense to, the way that they had already done it was that they were kexecing into it. And so I just decided to make it work the same way they were doing it. But I don't remember all the details for that. Because you've got to kind of carry the entire file system and everything you need, and you've got to write it back down. But you've got to do it as a file system. Like I said, it can be done that way, but I think we just decided that we weren't rebooting before, and I was like, I didn't want to make that requirement necessary. And it turned out kexecing isn't that bad, but it was a few weeks worth of work, definitely. And it was tricky, and I was like, well, I can make this work. So it was kind of like a lot of things, just a fun challenge, and thought rebooting was a little bit cheating, but...
Well, I don't see why it's cheating. I mean, it would also be nice that you have, like, you could, in theory, store the like the evidence of the process. Like you have this image that gets written out to disk at each stage of the process, which would also be nice for verifiability or trust or something. But I think it's fun. Yeah, K-second makes sense. I think it's really great that people are working on this. I remember when I was first getting into compilers, I thought it was just totally crazy that we can't. When I figured out, like, oh, at some point you just hit this wall in history where we don't really know what happened before this, and we can't trust. Like, at some point there was just this binary that someone ran somewhere, and that's where we got GCC from.
Yeah,
But
and
could you talk about your motivation for working on this? Like, what got you interested in this?
I had a similar experience, and I think what really kind of got me annoyed was I was working with a config format that I was kind of like, I want to do my own format, and I started doing parsers and parser generator, and I started using Antler.
Mm-hmm.
And Antler 4 is the latest version, and it's written as the result of running Antler 3. So Antler 3 is a parser generator which generates the Antler 4 parser, and it's all written around a parser generator from Antler 3. It's kind of confusing. And I was like, well, then how do I build Antler 3? Because I'm getting Antler 3 sort of like embedded in my Antler 4. Like the Antler 3 runtime is built into Antler 4. And I was like, wait a minute, that's like a jar file. Where's the source code for that? And I spent all this time, and I couldn't build Antler 3. Mm-hmm. Like, it was all these old libraries, and it was stuff, and I was like, really? Is this how this is just the way software is these days? You just can't go back, and you have to carry along this weight. And I'm like, well, how did the C compilers do this? And I started going down this rabbit hole, and eventually I was like, and then I stumbled upon this project. I was like Googling bootstrapping and all this stuff, and I stumbled upon this project. And I'm like, oh, they're like fully down the rabbit hole. These guys are nuts. And I'm like, but they're not nuts enough. Like, they haven't done their own kernel. Like, so that's where I kind of got into it.
So I remember that there's this paper, I think it's like a Turing Award lecture or something, reflections on trusting.
Yeah, Ken Thompson.
Yeah, Ken Thompson. I don't remember when that was written, but it's interesting that, like, we're just sort of getting to the point where we can do this now, in 2024.
Yeah, no, it was it's the same thing where it's like, God, no one's done this. You
Right.
can't, like, the GCC 1, Linux 1, all of that stuff. It's like hard to find those things anymore. Mm-hmm. And you have to and I should distinguish what we've done from like the software archaeology, where they really want to know what were the actual tools used. Like, they want to go get, AT&T System 5 Unix, and they want to recreate, and they want to figure out what was actually used. We're willing to we don't really care what they used back then, because it wasn't open source, and it's not practical to run VAX assembler anymore. And so we're just like, let's just create something that makes sense. And if you had, let me just be clear, the practical benefits of this are questionable. Like, maybe, because you can cross-compile from the latest software. You get a new processor, M4, whatever, you can just cross-compile from the latest stuff. You don't need to build up from, you don't need to write an assembler from scratch, to make use of a new so it's really more like, and some of the guys say, there's been the XZ backdoor and all that.
Reasons.
Like, they're legitimate reasons, but they're questionable. I think it's more like, it's just a crying shame that you can't you get back to a certain point. I think Nix is also like that. You get to a certain point where, because I was like, well, how do you, like everything's checksummed from some other thing, and like I think you get to something where it's just like, oh, you use the standard tool set, and it's not checksummed. And I'm like, well, okay, so they get to the point where they just punt and they just say, well, you got to start from somewhere. And every like Linux from scratch, or where there's all these different projects. At some point, they're like, get a C compiler and start from there. So it was more like just, again, I thought it was more of a challenge. I was just like, you know, I actually retired a few years ago, and so I was like, had time on my hands, and I'm like, I can write a kernel, like it'll be fun. And it was fun for a while. And then some of the things where it got really hairy, and at some point I got to the point where I tried to run make, and he uses pipes, and it's like has to have pipes and all this stuff internally, and I didn't have pipes in the kernel, and at some point I was just like, done, not going to do it, because you have to have two processes kind of like handing off between each other. And the way I had it working was I could spawn a process, it could run to completion and then come back to the previous process, but I couldn't have two processes kind of like I didn't have multi-processing really to have stuff running between a pipe buffer and all that. And I just like, there was no way to do it. So that's when I was like, okay, let's look for the next operating system we can build that's reasonable. And we looked at Linux 1 and all that, and it didn't really work out. And so, because all the artifacts are kind of lost to history back then. But this one guy started writing his own operating system with a C89 compiler, and he won't accept any code that's not C89 or lower. And he started like 27 years ago, and it's called Fuix. And one of the guys on Live Bootstrap says, well, maybe we can compile that. And then we're like, then I made it work. It took months, but we were able to then boot into that, which has like everything. Like it runs a full operating system, and then we use that to build Linux. So, but yeah, it was. But you know, it was what was needed at the time, and so I thought, like, you know, it's something to do, and they're trying to make it. They're trying to run everything on a UEFI shell now to build up of everything, and somehow they're going to have to port things to use UEFI primitives, because it has its own fat file system and so forth. You get a lot more to start with that, but still there's a lot to be done to make it work on that.
When you say primitive versions of C, do you mean like subsets of C?
Yeah.
Or like, oh, okay. Not like C89. That's not, like, more primitive than that.
Way more primitive than that.
Okay.
Yeah, so like, they're like, well, we'll support structures, pointers, function pointers, loops.
What is debugging like at like a stage? Like you need to debug like one part of it in the middle somewhere. Do you just like run the whole thing up to it and then just like cancel it? Like, all right, let's take it from here. Or do you guys have like checkpoints of like the different steps?
Debugging sucks because we don't have a debugger.
Oh yeah, that's
So I tell you, debugging a kernel that's running on bare metal without a debugger, it's difficult. And it's funny because there's one surefire way to get like information out of a kernel that's not behaving correctly. Like you want to see, did it get this far, or did it go haywire up here somewhere? And you have like, there are times when I'm trying to output stuff and I'm not even getting output that makes sense, or it's not working. And so what I would do is I'd stick a jump loop, just jump to itself, And then I'd look at QEMU on top and see if QEMU's pegged, then I know that it's running in that loop. Or if it's pegged already, like it's pegged and I don't know what happened, I'd put halt statements in. And I'd see, did it get to the halt statement? Because then QEMU would, so it's either a halt statement or a spin loop. And that's the only signal I can get.
Can you not single step QEMU?
Yeah, I do that too, but sometimes you're running millions of instructions and there's just no way to know where, like
No symbols.
you don't know where it happened. There's so many system calls happening like in the middle of this scheme interpreter. It's running for 15 minutes and at some point it just dies. And one of the hardest problems was that in that scheme interpreter, they had reserved an array for file descriptors. And the way I implemented the kernel was I just had an index into the file system, which is just a linear set of files. And I had really high file descriptors. And so it overran that array. And I had no idea that they had limited it to like 512 file descriptors where I had ones going into the thousands. And so it would just corrupt memory.
Yep.
It would just go off into corrupt memory. And yeah, those problems took just forever to figure out. But as an interesting side note, I was reading through some sort of like historical notes that Linus Torvalds said when he was writing Linux, and he said the exact same thing about using a spin loop or a halt statement to get a signal out of and I think he actually I don't know if he was using an emulator or something, but he knew whether it was spinning or not, or whether it had halted.
You can get one bit of information.
That's
out.
the only one bit of information you can get out of it. And he used the exact same method. I was like astonished, like, okay, well, but I was surprised that he wasn't using more advanced tools. But I guess there's certain circumstances where that's all you can work with. This has gone on way too long, Rob. Probably I've taken so much time.
Super interesting.
Yeah.
Oh.